So this is my story for last 30, 40 years. There is something I know. I have to get it across to impressionable young minds like you. And professors get in the way, and I don't know what to do. It's terrible. I'll have to tell you what's chaos. And it's elementary if you're learning it for the first time, and it's extremely hard if you are a professor. The worst thing that can happen to professor is understanding a new thing. No matter how much I try, I'm trying not to confuse you, so I'm trying just to use what's a rather nice book by Strogatz. And this was written in the 80s and 90s in prehistorical times. So here we are, chapter 10, and we are supposed to understand chaos. I will cover the same material as chapter 10. So what is chaos? And the problem with chaos, if you're an applied mathematician, is that for the last 8 or 9 chapters, we did stuff that applied mathematicians have done, and mathematicians, but especially applied ones since 19th century. So there are lots of no details all the time. It's an active field of research. There are more bifurcations every day, and there are more people who earn their bread talking about them. But chaos is something totally different. So far, the course has focused on order. What happens if you have something that's nonlinear, but basically there is one solution. Things like various nonlinear biological clocks we looked at. And chaos is not more of the same. It's actually understanding what Boltzmann and Maxwell did in the 19th century and what the modern statistical mechanicians did in the second half of 19th century and what they do today. And it is totally different than looking at a little nonlinear clock, kind of Salvador Dali's clock that's a little bit bent and hanging. What you have to learn is how to look at infinitely many solutions of your equations of motions, because that's what happens in turbulence. There is a precise meaning in which infinity, it's countable infinity, but it's exponentially many solutions for any resolution that you take to explain the system. How to take them together and put them together, it requires a new way of thinking. It's elementary, but it doesn't help to think like applied mathematician would think. It's not very helpful to think of ordinary differential equations, some nonlinear terms, and figuring out how to deal with them, perturbation series and whatever. It's just useless. Let me review where we are now. This is review of the previous chapter. We have made a jump from continuum, meaning time going in infinitesimal steps and differential equations being integrated, which is a part of a training of lots of engineers and other kind of scientists, to discrete time. And there is a logic to it. I'll just remind you what the logic is. So the idea is that if you have some long trajectory, so you start at x1, and you look at your system at time x2, and then you look at it at time x3, and then you look at it at time x4, you're replacing looking at the whole curve by stroboscopic pictures of where you are in some states. And the deep idea in dynamical systems is you don't do this by using external clock, like in a disco and strobing your dance. You actually use intrinsic properties of state space. Remember, state space is not coordinates x, y, z. It's a space of all possible states of your system. And that could be temperatures, that could be electrical charges in cells, neuronal cells, or cardiac cells. It could be quantum fields, it could be lots of stuff. But basically, the basic idea is that if you have one-dimensional curve in state space, you can slice it by codimension one surface, and you can divide the space into things that happen before and after you cross this codimension one space. And codimension one, we're in 3 dimensions, so it's 2-dimensional surface right now, but if we were in 4-dimensional, it would be 3-dimensional surface, has a property that you must cross it because it's a border. Now, if you try to divide 3-dimensional space by drawing a line, you would be a fool because there is 0 probability or trajectory hits a line, a 1-dimensional object. It can only hit objects which are smaller than that. The reason why this is done, you see the dynamics much better in Poincaré section than in a full space. But the deep reason is it's not very trivial when you're looking at dynamical time evolution, dynamical systems. But if you have a point, any place in state space, it has unique curve going through it, which if it's a short piece of it, we call a trajectory, from here to time 7 minutes later. And if you look at all possible times we can reach on this curve, that's called an orbit. It's a set that has a property that it's time invariant set, meaning that if I look at orbit 3 minutes later, all that has happened is points on it have walked along it, but the set has not changed. So that's a deep idea of the theory. This piece of spaghetti is known once you specify one point on it, and you want to know what happens to its neighbors. And that's why you cut it transversely. There is a little mathematics here, but it's not very important. To define something that has 1 dimension less than whole space, you can write some equation that says some function u equals 0. And that function could be a plane or it could be some curved surface, whatever you want. If you evaluate your trajectory on that function u, whenever it's 0, then you mark a point. So this surface, which is 1 dimension less than a whole space, is defined by a single condition, which reduces something that used to be d variable. Now it's d minus 1 variable because there's one condition. So you still have variables across. And now at every point of the surface, there is a normal to it, this little blue vector. And this blue vector you can compute. It's easy to compute. You've seen it lots of time, but basically if you do a little variation, it's given by the gradient, by derivative. And there are 2 things happening at that point. There is normal to the hypersurface, and there is your velocity vector, which you have defined at every point. Every point has an instantaneous velocity. You can distinguish the points that go up from the surface from points that go down. Like this one goes down. And the way you distinguish it is very simple. You multiply these 2 vectors, and if the result is positive, you're moving in the same direction. If the result is negative, it's going in the negative direction. So what you want to do is you want to find some typical point on the surface. That's an important point for you. And your neighborhood is defined by all points which are moving in the same way. And that defines a Poincaré cross-section. Example. When you do this for Lorentz flow, you have a freedom of what surface you use. The natural one is to use a hyperplane, which is now 2-dimensional in 3-dimensional space. And you have an invariant subspace. There is a z-axis, which is the rotation invariant. So you make that hyperplane cross it. But other than that, you're free how you do it. So you can, for example, cross it in such a way that it contains these 2 points. That's this thing. And you can now look at how you pierce it in one direction. That's this blue line. And ignore how you pierce it in the other direction, because those guys are totally different from you. They're going in the opposite direction, so they're not your neighbors. You can rotate this, and for example, if you take 2 sections, this section is very good to understand what happened close to the equilibrium, but the other direction is very good. This red dots is good to understand what happens when you hop. Now, Chaos Book tells you, but I won't do it, that this is stupid. You should quotient the symmetry. So instead of that, a chemist, an intellectual called Rosler, wrote an equation which didn't have these 2 equilibria copies of a discrete symmetry, had just one. And it's a simple equation. It's in Strogat's book. But it has a nice point. It has an equilibrium here, which is slightly repelling. So it's very much like this equilibrium. And that's why Rosler constructed it this way. So if you're close to that equilibrium, you rotate. And there's another equilibrium, which is not drawn in this picture. It's up here. It's a repelling equilibrium. So you get close to as far as you can get, then equation is designed in such a way that if you get a little bit too far, you get kicked very high up, and that other unstable equilibrium bends your trajectory and forces you to fall, and you just keep going and doing that. Here you can really understand what Poincare sections are doing. So you can just take some plane, like plane A, plane B, plane C, and plane D, which cuts the flow nicely. And down here, the floor is pretty much in a plane. So this looks like it's horizontal. When you look at it closely, it turns out that in these units, which are important units for you because that's how far this trajectory can go, it's not really flat, it's slightly curved. Now you get kicked up. So if you look at that Poincare section, it teaches you how you got stretched this way. And then you start falling back. That's what this Poincare section is. And this is just the radial distance. So it's pointing this way from 0 radius to out. That's why it's bent different way. And now what's happening is you're being squashed into the plane. So what happens is next time, you end up being squashed in this thing. And if you look closely, this is much thinner thing than before, but you have 2 parts of it. There's a part like this, and there is a part that's bent back. And if you now go back to where you started from, this gets contracted by 10 to the 14 or something, as far as I remember. So this turns out to be very thin. And that's what chaos does. What chaos does is it, in differential flows, but it's much easier to understand in Poincare sections, points that used to be close to each other along this line, their distance increases because you're being stretched. But you're not allowed to escape, in one rotation of this system, you're not allowed to escape arbitrarily far. There's some maximal height you can reach. And at that maximal height, you get folded. So there is like a fold here. And there is a part that's still close to the origin because, you have this whole line. So the part is still with you. And then there is the other part, which is folded. You can see the folding happening here. So you're being stretched and squinched. And there is a particular point that's called critical point, which is the folding point. This guy that you see very clearly in this Poincare section. And then you get folded, you get stretched, and you get folded. So what's going on? Locally, neighbors are getting stretched. The ones that are close around this folding point end up on different sides of the fold. And but you're not allowed to go very far away, so you get folded, you get scratched. And that means that the points that used to be very far from each other, on two sides of the fold, they get arbitrarily close to each other. So locally you're being stretched, but globally you can get arbitrarily close to any point on this attractor. So that's the essence of chaos: stretch and fold, stretch and fold. That's what's happening in all the systems. So you expand and then you mix, because you get things which used to be far apart very close to each other. And the important thing is what happens across the flow and not along the flow. What happens along the flow is rather boring. The important thing is captured by cutting the neighborhood kind of transfers to your flow and describing what happens to the neighbors. And that's how you get to Poincaré section. Now, you started with three-dimensional flow, but for all practical purposes, this Poincaré section is one-dimensional because it's so thin that you need a microscope. You actually have to go, in this particular example, you have to go to not even angstroms, but you have to go to Fermi's nuclear size distance. If you start with millimeter, when you come back, you'll be squashed to nuclear size distance. So it's not just that your printer is being crude here. You're really, really indistinguishably very close. So something that as equation looks like a differential equation where past and future is very well known, turns out to be not very predictable going past because of this crunching. And the effective dynamics is actually one-dimensional. This miracle. You start with 3 dimensions, you end up in 1 dimensions. This is obtained by reducing the flow to Poincaré section. Now, Poincaré section is weird because you're hopping finite distances. So what Poincaré section does is, you're here, but at the next iteration, you might be up or down someplace, so you're running all over the place. These points which are near to each other are not near to each other necessarily in Poincaré section because two very distant points can end up in the same place. So now what you can do, you can say, well, the important thing is just the radial distance. You can see it here. The important thing is how far am I from the equilibrium point at the center of this thing that organizes everything, because this equilibrium point is a complex eigenvalue pair that says I spiral out. And then it has a third eigenvalue which is attracting, which points into it. So that's what's causing this taffy being stretched and folded. So you can, look at it, and you find out that when you look at an intelligent version of it, like right here, which seems the most boring version, but that's actually a very good one. If you go from this and you come back and you plot where you end up, so for every point in this radial distance, you call that x, and it's return xn plus 1. And you plot that function. That function is well defined, and here it is. And it's very nice function because it's smooth, even though, when I look at how I get squashed here, that looks very singular. But if I actually look at distances along that radial line and look where I come back, I end up with something that looks, it's called unimodal map, but it's qualitatively like a parabola. Now you have to think a little bit more about it. You can have stupid sections, but I don't want to talk about it. When you run this system, that's what you get. You get this kind of smooth curve and everything is fine. And you might be surprised that modern mathematics has not proven that this is a strange attractor. So what's happening in the system is that initial point hops around on it. This thing is a strange attractor only if every trajectory is unstable. Now, we actually don't know where it's true because, the trajectories, this is local slope here, is the rate of expansion of the neighborhood, right? Because it's a one-dimensional map. So when I look at, it's just slope of the map that is expansions. But every so often I come arbitrarily close to this folding point where I actually have not slope like here, slope is 2 and maybe 4, roughly speaking, in one return. Neighbors get separated by factor 2 or 4. Here, this gets crunched by arbitrarily small factor. So all kind of flows that physicists care about have this property that they are smooth. And smooth means that their return maps are not necessarily under control. And it's quite possible that that system has an attractive orbit. Now, if that happens, you don't have chaos, because chaos means that everybody is unstable and everybody mixes with everybody else. But if there is a stable orbit, that thing, doesn't mix with anybody because it just has its own neighborhood. It's called basin of attraction, and stay where it is. This is a typical situation if you're looking at any system that you look in physics. Rosslayer is Lorentz is very strange because Lorentz has this cusp here, which has to do with presence of this equilibrium in discrete symmetry. So it's the rotational symmetry that says that that return map that you see here has a property that it's always stretching. There is no nice fold, because it turns out what Rosslayer does is it takes the whole neighborhood of trajectories and then it cuts them like with the scissors and excises this possible thing. But a typical flow that you meet in nature will look like this. And for that reason, no mathematician has proven that this system and many systems like this is actually an ergodic system. You have to understand that the things that you need to do as a working person have not been made rigorous by your colleagues which enjoy rigor. Well, let's understand these mappings. So for example, my friend and I, when we learned this first time around, we were worrying about the number of fish in a lake from year to year. There is a nice problem in ecology which says number of the fish in a lake. If there are few fish, there is lots of food, they grow. So there is a function year to year which is growing on this side. But if there is critical amount of fish, the next year, there won't be enough food because they have overgrazed the food, so there'll be fewer fish. And if you start with very, very many fish, they'll eat everything and the whole thing will die. So that's a nice thing in ecology. We saw a fake version of it called this Verhulst map, but in ecology it's iterative. You go and count the fish every summer or whenever. You go and count them, or the number of moths in a forest, and you have this kind of model. So that's what we were wondering. So for us, this made lots of sense that one look at it year by year. Why were we worrying about this? That you will learn in coming weeks. So that says, to understand dynamics, we can give up everything we've learned in the first 2 sections of the course, which are all these ordinary differential equations, and just look at discrete maps. That's all you need to understand. And indeed, if you read mathematical literature, they always say when they discuss ergodic systems, they don't use word chaos. They will always say blah, blah, blah of flows, meaning continuous in time. And then when you read, they'll immediately switch to the maps and do what we are doing from now, because the stuff along the flow is not very important. So what does one do? One looks at Poincaré section like this, and one realizes, this is now in d-1 dimensions. So these vectors can be 2-dimensional in cases I'm drawing pictures of. But this two-component vector maps into that two-component vector using two functions or vector of two functions. And when we do this for turbulence, we say, there is 1,000,000 minus 1 dimensions here, 1,000,000 minus 1 functions here, and we get the next thing. So the general setting is that you have a multinomial approximation. You have, some number of dimensions. And now ignore my definition of dimension, etc. But basically, you say, when I'm looking at a smooth map, then I can probably write it as a sum of linear terms, constant terms, and bilinear terms. And maybe I need to go a little bit further. And that's called Poincare return map in general. The simplest example of it's called a known map. A known map is what Lorentz is to weather. A known map is to Lorentz. It actually was invented by looking at Lorentz, but it's better motivated by what I just showed you, this Rosslayer system with these sections. But if the system is not so thin, doesn't have so strong contraction, which was designed by hand in designing the equation, you'll find out that this object retains the structure being folded, visibly so. This is captured by a known map. You say, I'm in 3 dimensions, I cut it by a hyperplane. So I need to define a 2-dimensional map with 2 components that maps me from the hyperplane back to hyperplane. And this is the best fit to my return map that I computed by painfully integrating the equation until the next point for all the points that I want to use to fit it with. And you end up with a very simple idea, which captures what I keep telling you. What these plots are doing is they're locally separating neighbors. So they're stretching. How do you locally separate neighbors? Well, you take a neighbor and multiply it by some number. Now, if you do this for linear systems, so if there was a linear term here, it's pretty boring because linear system stretch neighborhood ad infinitum, right? It's a linear system, so you just run off to infinity, not very interesting. So you say, let me now take not the linear x, but let's take the first nonlinearity, which is x squared. Now, what does x squared do? If you have points around fixed point that are moving to the left and to the right away from the fixed points, so going into the negative and positive direction, what x squared does is it identifies positive and negative. In other words, x squared folds them into each other. And then you have to couple this, it's 2-dimensional map, so you have to couple this to the other direction, and you play with it and you discover it's called a normal form. You've seen normal forms before a little bit, but for differential equation. Now it's a normal form of the map. Turns out this is kind of the simplest thing you can do. There is another coefficient, and it turns out that this coefficient is telling you how neighborhoods stretch. This coefficient tells you how they compress. And if B goes to 0, this becomes 1-dimensional map. It's parabola, that's the simplest thing. But if B is, let's say, -1, this turns out to be an area preserved map. And what you typically see as opposed to Rosslayer, here you seem to have 1-dimensional map. So you've lost invertibility because you've gone from 3-dimensional 1 and you don't know how to go back. But if you don't contract so strongly, that's a case where this B is, 10 to the -12 or something. So it just shrinks you. If you don't construct very strongly, you'll find out that as you come back, you produce a layer and layer and layer. And I show this on Danish television in a science program. In Denmark, we're very proud. I'm Danish, if anybody wants to know that. In Denmark, we're very proud of something we call wienerbrød, but Americans call it Danish pastry. What it is, you take some dough, you put some butter on it, and you press it, fold it, press it, fold it, press it, fold it. And it's a perfectly good example of chaos, because the nearby pieces of flour in the Danish pastry keep getting separated roughly by a factor of time every time you press it by a factor of 2, and then you fold it. And the far away pieces of grain become very close because you keep folding it. And this is what you get. Now, my colleague Benoit Mandelbrot decided to give a name to this. It was known for about 100 years before he named it, but he gave it name fractal, and it stuck. So, it's not a line, and we'll discuss what fractals in more detail. So this is how we went from determinism, meaning predictable future, to indeterminism in deterministic systems. If B is small, for all practical purposes, you cannot go back. And that means that, every future has 2 possible paths that end upon it. So you've lost determinism, at least reversibility. And that's one way of getting to chaos. So what chaos is stretching of the neighborhoods and folding. Stretching of the neighborhoods is characterized by a rate of stretching, which is called Lyapunov exponent. And folding is characterizing by, how many folds you make. So for example, when I tried to do it on Danish television, I was trying to fold once, but they brought a Danish baker from a little rustic village outside of Copenhagen, Bagermester Iverson, the great Danish baker, who always gets called to television whenever there is a children's show where they bake, because he has a cousin who works for Danish television. So he thought he was doing children's show, not science show, when he showed up. And he told me, that's not how you do Danish pastry. You stretch it by factor 3, then you fold it twice. And then you keep doing that, which is how the real bakers make Danish pastry. And what it means is that topological entropy is different, because there are 3 ways, 3 neighbors that get squashed together, not 2. So it has a larger entropy, and it has larger Lyapunov exponent because you have to multiply by 3 the length of the dough before you fold it. So it's a different dynamical system. It has different entropy, and different entropy meaning the logarithm of number of ways you can come back, and different stretching, Lyapunov exponent, which is a logarithm per unit of time, how far you get stretched. So chaos is positive Lyapunov exponent, meaning everybody is losing its neighbors, there is no love, and positive entropy, everybody is being flooded by strangers, which are coming from all possible directions. That's chaos. That's closer to our own experience of chaos. Let's make this a mathematics. This is how we got to the chaos, by studying dynamical systems we care about, flows, weather, chicken hearts, neuronal networks, deep learning, whatever you have to do for your life, turbulence. Now let's get the essence of it. So I told you that the essence was that we take x squared, because that's first nonlinear term. if you're trained in polynomials. But then I told you the main difference in X squared is that it treats the negative numbers differently from positive numbers. Positive numbers remain positive and negative ones get mapped into positive one. So I gave you a topological statement. I gave you a statement which is qualitative and it didn't depend on X squared. So it turns out that to have chaos, you don't need things to be described squares. It suffices to take the absolute value of something, have two outcomes. If my linear map was negative, I do this absolute value on it, and if it was positive, I don't. You'll see that it's called Dike map and it's in Strogatz. But I would make it even simpler. So the simplest explanation of what chaos is flipping coins. So that was first used by Bernoulli brothers, as to replace probability, which was very hard to understand in Laplace time or 18th century, by calculation, which is exact, but the output of it can be interpreted as random. And they had a reason to think this way because flipping coin is not a random process. If you describe carefully the exit of the coin from your hand, and my colleagues have done this for nice simulation calculation for Louisiana Danish Art Museum, where you actually flip literally a model of the coin. You do the equation where the coin rotates, flips, and hits, and then you have a result. So it's a deterministic process, but you know that it's 50-50 chance that face comes up and face comes down. So this is Bernoulli explanation. And because chaos is a new thing and a painful thing for my colleague to learn, I have to usually do it at least 3 times. So I will do the same to you. I'll do it once and maybe a little bit twice and 3 times. So this comes from Faust. We have to learn anything, to teach anything, we have to teach it 3 times. I gave you a qualitative picture that may be counted 1. But now let's do it as though this is 18th century. So here is what one of the brothers Bernoulli, I've lost track which one, said. Let's say that we have numbers from 0 to 1, and they are maybe related to the angle of the coin, so the coin is this way or that way. But it doesn't really matter what the real coin does. This is going to be a deterministic model whose effect will be the same as though we had random coin. So we say our initial state of the coin is specified by one number between 0 and 1. And now the stretching that happens is that as I flip it up in the air, this gets stretched by a factor 2. So now on original state was, and now you think of the baker Iversen and his dough, it's stretched twice. So it doesn't fit on a table, I mean, if I keep doing it, I'll get off the table. So what he does is he cuts it exactly at a half. And then he overlays the thing that was sticking out here over the whole things. And then I have 2 layers. But now, because this is a one-dimensional system, they get squashed into a line. So mathematically, what it is the first part, here is an equilibrium point, fixed point, it's a map, so it's a fixed point. The first part gets stretched by the map into a whole unit interval. That's what this does. If you get to the beyond the 1/2 point for initial point, you would be out of the thing. So that's cut off and slid back. And that's what modulo 1 does. So you have a linear map, but its effect is nonlinear because there is no way to describe cutting it into pieces as a linear operation. What that map does is if you repeat it once, guys, which are on the left-hand side, only half of the initial condition, the ones on the right-hand side of it there. But if I repeat it 2 times, then the things that are 1/4 here on the left-hand side will still be on the left-hand side after 2 iterations, multiplied by 4. The ones that were here in the first iteration will be still inside, but second time they'll end up on the right-hand side. So their future will be on the left, be on the right. The ones that started on the right-hand side close to here will end up being stretched out and thus covered 0. And the ones which are very hard here will end up stay on this right-hand side. And you can see that what this is going to do is that as you keep repeating, you'll stretch this thing by 2 to the n. You'll have to slice it to 2 to the n pieces, and you can give a name to each piece. You recognize that this name is actually a binary label of the thing. So binary numbers own intervals. You can also notice an interesting thing. There is a point here called 0 that never leaves. There is a point here that jumps between them. So you start here, you end up there, but you go back and you just keep doing this. So these guys contain period 2 point. There is a subtlety about a modulo 1 not including 1. So that point gets identified by 0, but that doesn't matter right now. That's a little bit too much mathematics. So that's called Bernoulli map. And now when you have a hang of it, there's no reason why to stretch by 2. Bairmester Iverson stretched it by 3. So you're allowed to put any integer here as a stretching factor and then take a modulo. Now, what's a modulo? Modulo says that a number multiplied by s could be larger than integer. In that case, I can take the integer part of the number and just keep what's left over. So integer part is called m. So if I subtract these 2 numbers, I'm guaranteed the next number is still in the unit interval and still on the table. And I can now replace a linear operation by a nonlinear operation saying, in next step, I want you to be in one of these intervals. For example, if s is 6, I can choose any sequence of these m's to tell me where am I. And they will, label these subintervals. So in one iteration, unit interval gets divided in 6. In the next iteration, I won't do it, but you can see there'll be 36 things. And determinism is there because every one of this interval has a name. That's called symbolic dynamics. But as we go further and further, these intervals get exponentially smaller, and we have exponentially many ways of coming back. So the slope of this curve is called Lyapunov exponent. It's logarithm of the slope. And the number of possible ways you can go through this flipping sequence is called entropy. You take its logarithm divided by n. Here you took the iteration and divided by number of iterates. And that's chaos. That's the essence of chaos. So chaos is positive Lyapunov minus positive entropy. Lyapunov says, how fast is local escape? Entropy says, how many ways of getting back? And that is deterministic chaos. Now, some interesting things have happened in the process. You actually know a lot about unit intervals. So you know that unit interval is populated by numbers of various kinds. So by the time you're in high school, you know that beyond numbers 0 and 1, there are things that are called rational numbers. So what fraction of an inch do I have to specify some small interval, which is precision of my calculation. And if you compute the numbers, which are called periodic points, which are intersections of the straight line with a diagonal, these are the numbers that will, just run around and not go off to some strange infinite sequence. It'll just repeat itself. In this particular case, they happen to be rational numbers. You can compute all these periodic points analytically. So what's going on is it says in chaos, everything is possible if I go far away. But the way to do an organization of chaos is compute these rational numbers, these guys, and then assign an interval to them. And that's what we always do in practice. We have our measuring stick, and then we say it's 37.3 millimeters, but which we mean there's an interval which is pinned down, which is 0.01 millimeters by that measurement. So in practice, this is extremely important. It says that these periodic points are the skeleton, the markers with which you will measure out the space of all possible behaviors, because in general, any normal number will have a different sequence of hopping around as you iterate this map. And that will carry to non-linear physics, where you cannot do this analytically, you have to do real calculations.